Welcome everyone to our today's lecture on Introduction to Black Hole Thermodynamics. So our lecture is from Satish. The slides are from Satisha Iso K. Let us begin with our today's lecture. So I would like to suggest that today's lecture is rather advanced, and if you are a beginner in the terms of cosmology, it will be quite difficult for you to understand the lecture. So I will try to keep it simple, but once again, it's rather advanced, so I would recommend you to just watch something from the beginning and then come back. So let us start. Mm, just a second, please. Okay. So how do we are going to continue with this? So what is the plan of our entire lecture? At first, we'll have the overview of black hole. BH is black hole thermodynamics, the causal structure of the event horizon, Hawking radiation, and string picture of the black hole entropy. Hawking radiation via quantum anomalies, and the universality of Hawking radiation. Conclusion. A third will be conclusion. That will be towards quantum nature of space-time. So let us begin with it. So overview of the black hole thermodynamics. So as you see, this is a star, and when pressure caused by nuclear fission in the star stabilizes it against gravitational collapse. In this nuclear fusion, when there some gravitational pressure is created due to nuclear fusion, you see that the pressure is both going outwards and inwards. So you see it's the collision of outwards and inwards pressure due to gravitational collapse. All nuclear fuel that has been used up. So massive stars and their lives by supernova explosion and the remnants become black hole. So these stars explode by a supernova explosion. There are multiple types of explosion. We have discussed about it already. So one of them is the supernova explosion. So when they go through the supernova explosion, the remnants of the star convert into a black hole. The no-hair theorem. So before continuing the no-hair theorem, you need to understand the Q tau and O zero. So stationary black holes are characterized by three major quantities. These are mass, Q for charge, and J for angular momentum. Then we have the Schwarzschild black holes. Schwarzschild provide a horizon radius, and this is an equation. So for ds square equals to f of r dt square minus dr square over f of r minus r squared d omega squared. To find out the radius of the horizon, event horizon, we use the Schwarzschild radius equation, that is RH radius of the horizon, that is 2 gm, 2 gravitation mass over c squared, that is speed into the light times speed into the life itself. So speed of light, sorry, forgive me please, speed of light squared. Then we have, so for Schwarzschild black holes, f of r, the value of f of r function that we are seeing, this is 1 minus r of h over r. The curvature is r nu v rho sigma by r to the power nu v rho sigma. So this curvature, so the curvature for this, so according to Schwarzschild black hole equation, the curvature is equal to 12 r squared h over r squared r to the power of 6. So curvature is singular at r when r equals to 0, but we see the statement curvature is singular at r equals 0, but nothing is singular at the horizon. So when we are looking over at the curvature of the black hole radius, black hole event horizon, that can be singular at r to 0, but at the horizon, nothing is constituted under single. At horizon, the curvature itself is not singular. So the casual structure of the horizon, so we use the tortoise coordinates to mark them. That is r star equals r plus rh plus ln. That is bracket of r by rh minus 1. So to mark this or this coordinates will go somewhere over here. Null coordinates for this would be u equals t minus r star, where v equals t plus r star. And then we have ds squared is equals to f of r. We see the previous equation. F of r where we had dt. So what? Just a second. So yeah, f of r squared, I guess. No? Yeah. So we had dt squared minus ds squared minus r squared d omega. So that would be equal to f of r d du dv subtracted by r squared d omega squared. The critical coordinates are as follows. That is u equals negative 1 over k and its exponent is negative ku, whereas the v for it is 1 over k exponent k v. And for the surface gravity, the equation that we use is k equals 1 over 2 rh. That is equals to gm over r squared h. And then we have d square equals rh over r. See, by e minus r. Just a second. Okay, I'll have to look at my laser pointer. Negative r by rh. Du dv subtracted from the r from r squared d omega squared. That is for the regular at horizon. So my question to you is, it's a very basic question. What is an event horizon? We all considerably generally talk about it. Kindly answer me in the comments. So okay, so we see u equals 0 and v equals 0 at horizon. So where u equals 0 and v equals 0. So u equals 0 would be future horizon, where v equals 0 would be for past horizon. Horizon is a null hypersurface, and no one can come out of the horizon. You say light cannot even escape a black hole. We often generally say this statement. So for r of h equals 2 gm, so for the horizon, and we take the black hole's mass always increases classically, and horizon's area never decreases like entropy in thermodynamics. So dA is greater or equal to 0. So analogy with thermodynamics, that is equilibrium thermodynamics is for black hole. The zeroth law. So we are taking analogy with thermodynamics, and then we have equilibrium. We have here equilibrium thermodynamics and black hole to match them both. The zeroth law is for T equals constant, whereas the zeroth law for black hole thermodynamics is K is constant. The first law is dE equals T ds, whereas the first law of the black hole thermodynamics is dm equals K by 8 pi g dA. Second law is ds is greater or equal to 0, where the second law is dA is equal or greater than 0. Classical correspondence. Now we come to Hawkington radiation, one of my most favorite paths. So in 1974, Hawking found that black hole radiates this really black hole emits a radiation which also the Hawking temperature that was T of h or h bar k by 2 pi. I also have a paper published on trying to solve this black hole thermodynamics by introducing a function of I of t. So make sure to check it. I'll try to put the link in the description. So in 1974, Stephen Hawking gave an idea of the black hole thermodynamics. Not sorry, black hole thermodynamics, Hawking radiation. On the event horizon, there is a radiation called the black hole Hawking radiation. This Hawking radiation radiates any matter that is incoming inside of the black hole. The equation for this was T of Th is equals to h bar k by 2 pi. And entropy for the black hole is SBH. This was the Bekenstein formula. So SBH BH black hole, S is entropy. A over 4 H bar G, that will be equal to A over 4 L square PL. These all are quantum effects. Now what will happen with after Hawking released his paper? A very big problem came to our eyes, that was the black hole information paradox. Under quantum mechanics, information can neither be dissolved, neither can it be created nor destroyed. But Black hole radiation, Hawking radiation, is radiating the information of the particle. That means it is destroying it, eventually violating the law. And my paper is also trying to, aiming to solve this. So let's see how many of you can look for it. Okay, sorry. So for black hole that have the mass of 10 solar masses, so for that we have T of temperature of H, that is very low temperature, that is 6 into 10 to the power 9 Kelvin. Whereas for an entropy of the black hole, that is 10 to the power 79 kV. So that is huge entropy we can see from the number 10 to the power 79 is 79 zeros after 10. And for example, the entropy of sun is 10 to the power 58 is 10 to the power 58. So you can compare the differences between both of them. The classical limit for TH is 0, where the entropy for the black hole is infinite, which means the temperature cannot be more than 0, but a black hole entropy can go till infinity. And as you can see, this is a tilted 8. This is not an infinite sign. So, Easter egg. And now we have Hawking radiation, universal quantum effect for matters and black holes. I've explained all of this to universal quantum gravity effect, geometrical quantity. I've explained this too. Then we have physical picture of the Hawking radiation, where we see the virtual pair creation of particles. This is negative E, that is E, and X over X, that is the real pair creation. This is the virtual pair creation. In the black hole, this is if considered to be black hole. So the thermal spectrum with T to be over here, this is mentioned. KBT will be equal to H bar C cube over 8 pi GM. Now, derivation of Hawking radiation by Ura for eternal black holes. So it is a very broad spectrum of equations for Boltzmann vacuum and for Unruh vacuum. Both of them see as B, but most of them generate the constant of theirs differently. Sorry. If you're a cosmology student, I would really recommend you to just click a screenshot of this slide. Okay. Hawking radiation reduces the black hole mass as area decreases, and the second law is violated. The generalized second law is total is equals to is entropy of the black hole plus entropy of the radiation. So d of S total would be equal or greater than 0. So microscopic statistical meaning of black hole entropy. Thermal Hawking radiation contradicts the unitary evolution of the quantum states, information paradox, which I told you about. And microscopic understanding of black hole entropy needs quantum nature of space-time. The basic idea to understand BH entropy in strings is that strings, both of matter strings and space-time, the gravitons, are excitations of strings. So when we take the four-dimensional Newton constant, that is G to GSLS squared, so over here you can see the string and whatever that is. So at strong coupling strings with masses of m, that then become BH black hole when its Schwarzschild radius equals the string length. So 2gm is somewhere over to ls. So S entropy is equals to kb log nm equals to kb lsm by h bar to kb gm square by h bar g equals to sbh, and n of m equals to exponent is is m by h bar. Just a second. We have a lot of it. Well, I think we have how discussed a lot of it today. To further continue, I'll upload all of this in part 2. Till then, bye.